If you hire like 3 painters to help you finish painting a house, the job gets done faster.
Right. Yeah, obviously. It's just simple math.
Right. But in software engineering, if you hire 3 coders to help finish a late project, it will actually take longer.
It's totally wild, but yeah, that is a proven fact.
Welcome to this personalized deep dive. Today's mission is to unpack a really fascinating stack of university materials that outline the fundamentals of how software is actually built.
And it is definitely not what most people think.
Exactly. Because you, as someone who loves learning and interacting with technology all day, you might think of software development simply as, writing code, like just a person at a keyboard typing away.
Right. The classic movie hacker montage.
Yeah, exactly.
Yeah.
But we are going to completely dismantle that idea today because building software is a fundamentally different challenge than building a bridge or like a skyscraper. The rules of physical engineering just do not apply.
They really don't. I mean, when you build a physical structure, you are constrained by the laws of physics and material limits.
You're dealing with concrete, steel.
Exactly. Things you can see, touch, measure. But software is entirely different. It is what the foundational literature brilliantly describes as a brain product.
A brain product. I love that term.
Right. It's pure thought. It's logic and imagination manifested into this highly complex architecture. And because it's completely intangible, the engineering required to build it successfully defies almost all traditional project management logic.
Okay, so let's unpack this, because before we can even explore the problems of engineering software, we have to look at the anatomy of the product itself.
Which is way more than just code.
Right, it's far more than just machine-readable instructions for a processor. If I write a quick script that says, print hello world, I mean, that's code, but it isn't a software system.
Not at all. The machine-readable instructions, like the actual code executing on the processor, that's just the raw material.
It's the brips.
Yeah, just
Have
the
you-
bricks. As a fully realized product, a software system is this vast collection of intercommunicating components.
Meaning what, exactly?
Well, it includes the configuration files that set up its environment, the system documentation that explains how the underlying architecture runs, and the user documentation that explains how a human is supposed to actually interact with that.
Right, so if you don't have all of those pieces functioning together in harmony, you don't have a software product. You just have an isolated string of commands.
Exactly. And the sources point out this fully realized product comes in 2 main development flavors.
Right, I saw that. You have generic software, which is, developed to be sold to a general open market, like a standard word processor.
Right.
And then there's bespoke or custom software, which is built for a single customer according to their exact specifications, like an internal database for a specific hospital.
Exactly. But what's really crucial here isn't just who buys it, but the strict hierarchy of what the software actually does. You really have to think of software as a layered ecosystem.
Like a cake.
Kind of, yeah.
Hmm.
At the very bottom, you have system software. This is the foundation. We're talking about operating systems, system utilities, performance monitors.
The stuff the user rarely sees.
Right, and the programming language translators themselves. This software is designed to operate and control the computer hardware directly. It manages the memory, the processor cycles, the physical disks.
And then sitting right on top of that foundation is the application software.
Yeah, the frosting on the cake.
Right. These are the programs designed to carry out specific operations for a user. Your word processors, your database management systems, your web browsers. And the dynamic between these 2 layers is where the complexity really starts to reveal itself.
Oh, absolutely.
Because the application software entirely assumes that the system software beneath it is perfectly stable.
Which it often isn't.
Right. If the underlying operating system updates or, say, changes how it allocates memory, the application logic resting on top of it can completely shatter, even if the application code itself hasn't changed a single character.
And that invisible dependency is the source of endless engineering nightmares.
Mm-hmm.
And, what's easy to forget is that the vast majority of software isn't even running on a desktop or a phone at all.
Really? Where is it?
It's embedded. Numerically speaking, embedded control systems, which is software that manages specific hardware devices, are the most common type of system in existence.
Ew, like the anti-lock brakes in your car.
Exactly. Or the internal logic of a commercial jet engine. Or even just the smart thermostat on your wall.
They are everywhere, just quietly managing hardware in the background.
Yep.
But taking a step back, whether it's an operating system or the code running your brakes, the fundamental nature of the product is identical. It's an invisible architecture.
Invisible architecture, yes.
I was thinking about it, like this building software is like building a house where the foundation, the plumbing, and the paint are all completely invisible.
That's a terrifying thought for a home buyer.
Right. Which brings up a massive conceptual issue. If the product is intangible, how do you even know when you're done building it?
Well, that is the ultimate existential question of the industry, honestly. With a physical house, you can point to a missing roof.
Yeah, the customer can literally walk in and say, hey, there's no drywall here.
Exactly. But with software, much of the process of creating it and the product itself is totally invisible. This intangibility means it is incredibly difficult for a customer to specify their requirements completely at the start.
Because they don't even know what's possible.
Right. And it's equally difficult for the developer to fully understand what the customer actually needs. I mean, you are basically trying to describe a cathedral made of air.
Because they can't point to the missing roof. And that perfectly illustrates why the traditional rules of engineering and project management just completely fall apart here. Large software systems are usually designed to solve what the sources call wicked problems.
Yes. And a wicked problem isn't just like a difficult problem.
Right.
It's a highly specific term in engineering.
It sounds so dramatic.
It is. It refers to a problem where the requirements are incomplete, contradictory, and constantly changing. Furthermore, in a wicked problem, there is no definitive right answer.
And attempting to solve one aspect of the problem often reveals or creates another distinct problem, right?
Exactly. It's like a hydra.
So give me a concrete example of a wicked problem in software. How does that look in the real world?
Okay, think about designing the dispatch system for a fleet of emergency vehicles.
Okay, high stakes.
Very. Now, the software needs to be incredibly fast. That's a core requirement. Lives are on the line.
Makes sense.
But it also needs to be highly secure because it handles sensitive medical data, high PAA compliance, all that. That's another strict requirement.
Right.
But adding heavy encryption for security mathematically slows down the processing speed.
Oh, wow.
So solving the security requirement actively damages the speed required. It requires a massive amount of coordination across different engineering disciplines, and there are almost infinite possibilities for design trade-offs across all those invisible components.
And I imagine the communication gaps there are a massive hurdle too,
Yeah.
because developers often lack the specific domain knowledge of the clients, right?
Oh, entirely.
Like, a software engineer isn't a paramedic, and a paramedic isn't a software engineer. They are essentially speaking completely different languages, trying to solve a wicked problem in an invisible medium.
It's a miracle anything gets built at all, honestly.
Which actually leads us back to that incredibly counterintuitive hook we started with.
The mythical man month.
Yes. The idea that adding personnel to a project does not necessarily increase productivity, and crucially, adding personnel to a late project will just make it even later.
It's one of the most famous observations in software engineering, and it all comes back to that intangibility we were talking about.
Right, because here's where it gets really interesting to me. If I'm behind on painting my house, hiring 3 more painters objectively speeds up the job. I hand them a brush, point to a physical wall, and they start painting. The overhead to get them working is almost zero.
Yeah, physical work scales linearly.
Right. So why does adding more programmers to a late project make it slower?
Because software is a highly complex architecture of logic. When you bring new programmers onto a late project, they don't know how all those invisible components intercommunicate. They don't know the thousands of micro decisions and trade-offs that have already been made.
So they basically have to stop and learn the whole history of the project.
Exactly. And who has to teach the new programmers?
Oh, man. The original developers who are already desperately behind schedule.
Yes. The original team has to stop writing code to bring the new team up to speed. They have to explain the design architecture, teach them the specific domain knowledge.
So they are essentially downing their tools to become teachers.
Exactly. But it's not even just the teaching time, it's the complexity of the communication itself.
What do you mean?
That's the real mathematical trap, is the exponential growth of communication paths. If you have a team of 3 people, there are only 3 lines of communication between them. A talks to B, B talks to C, A talks to C.
Right, easy enough.
But if you throw 7 more people onto that team to speed things up, you now have 10 people. You don't have 10 lines of communication. You have 45.
45.
Yeah. Keeping everyone synchronized on an invisible, constantly shifting architecture creates an administrative and communication overhead that just mathematically crushes the project's velocity.
Yeah.
That massive transfer of invisible knowledge drags the whole timeline down even further.
Okay, so if we know a project is going to get slower when we add people, and we know the requirements are always shifting because we are solving wicked problems,
Mhm.
how do businesses actually budget for this? It feels like an economic black hole.
It often is.
Yeah.
And the economics of software are actually completely inverted compared to hardware.
Inverted how?
Well, over time, as technology develops, hardware gets cheaper and more powerful. We all know that. Your phone today is cheaper and better than a supercomputer from the 90s.
Sure.
But software development costs are increasing rapidly because the systems we are demanding are becoming exponentially more complex. Software costs now frequently dominate the overall computer system costs.
Wow.
Yeah, if you look at a major enterprise system, the cost of the software running it will far, far exceed the cost of the physical server racks it sits on.
Okay, but here is the ultimate paradox of this industry that I saw in the sources. Maintaining the software costs exponentially more than building it in the first place.
Oh, by a huge margin.
For systems with a long life, the maintenance costs can be several times higher than the initial development costs.
Which brings us to the core issue of how these systems actually fail. Because to understand why maintenance is so expensive, we have to look at failure curves.
Okay, let's break that down.
Let's look at physical hardware first. Hardware follows what engineers call a bathtub failure curve. So if you imagine a graph where the bottom axis is time and the side axis is the failure rate.
It starts really high on the left, what they call infant mortality. Things break early because of manufacturing defects, like a bad solder joint or a faulty capacitor.
Right, exactly. But as those defective parts are swapped out and quality improves, the failure curve drops down and stabilizes. It becomes this long, flat bottom of the bathtub. The hardware is just stable for years.
Until it gets old.
Right. Eventually, the physical materials degrade. Metal rusts, plastic becomes brittle, heat warps components. They reach the wear-out stage, and the failure rate spikes dramatically back up on the right side of the graph. It forms a U-shape, a bathtub.
Okay, I can visualize that. But software is not manufactured, it's engineered, it's pure logic.
Right.
Wait, so if it's pure logic and never physically degrades, shouldn't a perfectly written program from like 1995 still work flawlessly today?
In a vacuum, yes. If software doesn't wear out in a physical sense, its ideal failure curve starts high because of undetected bugs, drops down as those are patched, and then just stays perfectly flat forever. It never hits a physical wear-out spike because logic doesn't rust.
But we don't live in a vacuum.
We absolutely do not. The environment the software operates in and the user expectations are constantly changing. Hardware is upgraded, connecting systems are updated, security protocols shift.
The target is always moving.
Exactly.
Hmm.
The target's always moving, which means you are forced to update the software just to keep it functioning in a new environment. And this is where the actual failure curve for software comes in.
And it isn't flat, is it?
It is not flat at all. It features severe, violent spikes all along that timeline.
So what does this all mean for you, the listener? Let's use an analogy here. Think about hardware like a regular pair of shoes. Eventually they wear out, they get holes, you throw them away. Bathtub curve.
Right.
But software is like a magical pair of shoes that never wear out. But every single time you try to change the color of the laces, the soles suddenly fall off.
Yes, that is exactly what happens. The spikes happen because of change. Software is uniquely elastic. The replication of it is trivial, so it gradually becomes more and more complex as changes are made over time.
It's like you're constantly messing with the DNA of it.
Exactly. When you introduce a new feature, or even just make a small change to a few lines of code, it can create totally unexpected side effects that radically alter the entire system's behavior.
Because all those invisible components are deeply intercommunicating. You change the memory allocation in the system software, and the application software on top suddenly drops the database connection.
Precisely. You change one thing, and a seemingly unrelated component on the other side of the system just fails. The system becomes unstable not from age, but from the continuous compounding addition of new features and patches.
So it's not dying of old age, it's dying of complexity.
Yes. The foundational literature highlights two main reasons why software projects ultimately fail. Increasing system complexity, because we are demanding larger, faster systems with capabilities previously thought impossible, and the failure to use proper software engineering methods to actually manage that complexity.
So how do we tame this beast? If software is an expensive, invisible product that costs a fortune to maintain and mathematically spikes in failure every time you try to update it, how do we stop the whole thing from collapsing.
Well, this is where the actual engineering and software engineering comes in.
Yeah.
You cannot develop good software simply by knowing a programming language.
Right. Sitting down and just writing code is a guaranteed path to a disaster.
Absolutely. You have to follow a proper approach. You need a rigorous software development methodology.
Okay. And a methodology is essentially a framework used to structure, plan, and control the life cycle of the software product.
Yes.
And the core activities of a typical process are specification, implementation, validation, and evolution. But what I really want to dig into is the how. How do you actually validate invisible components? How does a methodology structure pure thought?
It structures it through rigid abstraction and isolation. Because you can't see the product, methodologies rely on creating simulated testing environments.
So you don't mess with the live version.
Never. You never change the live system if you can help it. You build an exact digital replica, make your changes there, and run thousands of automated tests to see if anything falls over. Methodologies also enforce aggressive version control,
Meaning what?
meaning every single change is tracked and can be instantly reversed if an unforeseen side effect occurs.
You essentially build a safety net for the elasticity.
Exactly.
And that methodology is designed to ensure the final product possesses 4 key attributes of good software. Let's really look at these because there is massive tension between them. Number 1 is maintainability. Software must be written so it can evolve to meet the changing needs of customers.
And this is paramount because, as we just established, change is what causes software to fail. If a system is not maintainable, if the code is so dense and interconnected that no one can safely read or alter it, every change guarantees a massive failure spike.
But making something highly maintainable takes intense foresight.
It really does.
Now, the second attribute is dependability and security. This includes reliability and safety. Dependable software shouldn't cause physical or economic damage in the event of a failure, and malicious users shouldn't be able to access it.
Right.
But here is where the tension comes in. Making a system incredibly secure, requiring multiple authentications, heavy encryption, isolated networks, that directly fights against the fourth attribute.
Acceptability.
Exactly. Acceptability means the software must be understandable, usable, and compatible for the target audience. If you make a system so secure that it takes a user 20 minutes and 5 passwords to log in,
It's useless.
right, it is highly dependable, but completely unacceptable. It fails as a product.
And then there's the third attribute, efficiency. Not wasting memory or processor cycles. That also fights against maintainability, doesn't it?
Oh, all the time. Sometimes, the most computationally efficient way to write a piece of code is also the most incredibly complex, unreadable way to write it. It runs fast, but the next engineer to look at it won't be able to safely update it. You're highlighting exactly why this is a wicked problem. Balancing maintainability, dependability, efficiency, and acceptability requires constant, rigorous engineering trade-offs.
It's a high wire act.
It really is. And if we connect this to the bigger picture, think about why these methodologies exist in the first place. I want you, the listener, to just think for a second about a piece of software or an app you absolutely hate using at your job. We all have one.
Oh, everybody has one.
Right. It's clunky. It constantly breaks when you click the wrong button. The interface makes no sense. Chances are it's failing the acceptability test, or maybe the developers just drifted into creating it without a proper engineering framework.
Drifted is the perfect word there. Companies often just drift into software development. They have a service, they need an internal tool to manage it, so they just have someone write a quick program.
They skipped the engineering.
Totally. They skip the professional methods. They don't consider the long-term maintainability or the automated testing environments. They just start writing code. Consequently, their software is incredibly brittle, astronomically expensive to maintain, and completely unreliable.
Right. They get hit with that inverted economic reality where they are spending millions just trying to keep the system upright as the environment shifts around it. Professional software development is a systematic approach. It considers practical costs, schedules, and those 4 core attributes from day one.
It is a monumental engineering challenge, arguably one of the most complex human endeavors, precisely because the material you are working with is pure thought, layered over constantly shifting physical hardware.
Okay, let's briefly recap this journey we've been on because we've dismantled a lot of assumptions today. We started by redefining software not just as lines of code, but as an intangible brain product comprised of communicating components, environments, and documentation.
And we explored the counterintuitive math of the mythical man-month. Why throwing more people at a late, invisible project actually mathematically slows it down due to the exponential explosion of communication paths.
We also saw how the economics of software are completely inverted compared to hardware. Because of the sheer complexity of wicked problems, software costs dominate system costs, and maintaining that invisible architecture costs significantly more than initially building it.
And we finally understood those fascinating failure curves. Hardware is a bathtub that eventually rusts and wears out. Software never wears out, but it's elastic. Its failure rate violently spikes every time we try to change it because of unforeseen side effects.
Ultimately, surviving all of this requires strict professional methodologies, simulated testing, version control, and balancing the intense tension between maintainability, dependability, efficiency, and acceptability.
It is a delicate, ongoing balancing act just to keep the digital world functioning.
And that leaves us with a final lingering question to think about. There is a concept we touched on briefly: systems of systems, which are incredibly complex applications composed of a massive number of other intertwining software systems.
Right.
Now, we know that software fundamentally never wears out, but its failure rate spikes every time a new change is introduced to its environment. So what happens decades from now?
That is the scary part.
Imagine a future where our entire global infrastructure, our banking, our power grids, our automated transportation is running on millions of intertwined, constantly updating legacy systems of systems. Code stacked upon code, written by engineers who are long gone.
Just massive invisible towers.
Exactly. If every single change introduces the risk of an unforeseen side effect, are we building a beautifully immortal digital world, or are we just layering on so many unseen dependencies that an unpredictable, cascading massive failure is mathematically inevitable? Something to think about the next time your phone courses an update.